Okay, I'm hoping we can take up where we left off. I had to erase some videos that my son made. Alright, so glacial settlement at melt. Form in place are the old mountain ranges where rock is exposed. 5 years old, maybe more. So then we get into the soil orders, and we kind of covered this, so I'm not going to go into this so much. But I do want to cover just a wee bit on, we decided we're going to learn all of the 12 orders. I like that. I like that. The most productive soils: forest versus prairie. We talked about this. So why is the prairie? It's the grasses, right? And we talked about the roots go down deep, they slough off, they leave behind dead, decaying material for other organisms, for pockets of air, pore space. So they have great structure, soil structure. They have infiltration, meaning the water doesn't stand on top, it goes on down. They have great water holding capacity. So water holding capacity, they can hold water. And then mollisols, we have 22% of the entire order of mollisols in the United States. The second most productive is alpha sol. We have 18 to 19% of that world's order. Sounds extra special, right? So we have a lot of great soil. So it's not just the order, meaning like what determines why these soils are so different really is the biology. And then just to recognize that it is really only in these two fabulous orders, as well as other orders, obviously, it's really just that top 30 to 40 inches that we farm. I think on my apple peel example, I said the top 5 feet, so that's 60 inches, but really we only utilize that top 30 to 40, maybe 60 inches for our crops. Below that, prehistoric. Again, I mean maybe not prehistoric, but that's what they actually said in the video, movie, whatever, film. And this is an important one. You'll pick this up in the book as well. I think this first go around is 50% of our soil is solid. So, parent material, organic matter, clay, sand, silt, so on and so forth. The other 50% is pore space. And there's macropores and micropores. And the macro and the micropores are there for air and water. And not just water holding capacity, but water vapor. And this is also where the organisms live, the biology. And then that was that bit with Elaine, Dr. Elaine Ingham, and Dr. Elaine Ingham talks about the fact that the biology in the soil is like Times Square all the time, it's always active. And then Dr. Hansen recognizes that a gram of soil has so many microbiology in it, so much microbiology in it, that 70 to 80% of it we still have yet to identify. And these organisms, well, really the whole driver of the entire system is photosynthesis. Obviously, we need the sun for that. then the organisms are really what's making plant available nutrients. So you'll hear other language used in the videos that you'll watch about, CEC providing, plant ability to uptake nutrients, but it really is about the organisms. And it's those exudates that they're putting out there. She referred to them, Dr. Ingham referred to them as cakes and cookies. They're putting it out there to attract the bacteria and fungi. And there are 1 million bacteria per teaspoon of soil, miles and miles of fungi, and that is all to protect and to put up a wall to protect the plant from other intruders coming in, the bad organisms. Alright, then the release of nutrients in the plant available form, again, is the biology. We're also recognizing that, and we'll talk about pH, because pH in the soil is important, but there's also an oxidation and reduction cycle that occurs, and again, that has to do with the biology. But the oxidation and reduction cycle, and the reason I'm bringing it up in concert with pH is because sometimes we say that the pH is, I don't know if I'd say it's the most important thing. I definitely don't. I personally don't say that, but some literature might say that it is the most important signifier of whether or not plants can grow in that space or in that soil. But we're learning that the oxidation and reduction cycle is playing a big role, and that, again, it's driven by the microorganisms in the soil, because they're breaking down the carbon and releasing it, plus they're releasing nutrients for the plants to use. And the carbon in the atmosphere is reduced via photosynthesis, and it is released back by oxidation, again, driven by the organisms. Phosphorus, I talked a little bit about phosphorus being one of those, phosphorus. I talked about phosphorus being a little bit of an outlier because it is leached on a regular basis, or leaching is not the right word. It's removed from the soil system through erosion because it's so tightly bound to the soil particles, which is the complete opposite of nitrogen. So if we want to look at leaching in the soil, nitrogen and phosphorus are the ones that we lose. I want to go away from leaching. Nitrogen is leached, where phosphorus is lost in erosion. It could be just wind erosion. Happens all the time, happening right now. Where just tiny fine particles are lost, and those particles are bound with phosphorus at times. And due to that loss of those two nutrients, it's part of the reason why we apply so much of those two nutrients. If we understand our soils, we can apply less nitrogen. But historically, phosphorus has been applied in excess, just because we know that it's really challenging for the plants to take it up. Maybe not so challenging for them to take it up, but it's challenging for them to access it. So they have to put their root hairs out there further in order to get the phosphorus to them, which is why fungi, mycorrhizae, send out their fungal hyphae and add to the root hairs. So if a plant has these, major roots, their primary, secondary, and tertiary roots, then they have secondary and tertiary, and then they have these tiny little root hairs that extend further out to find phosphorus, or to mine it, really. It's also in rocks in the lithosphere, but again, the fungi can tap into that from the rock as well. The other way we get it is to mine it, and that's our doing as humans, which is where we get our rock dust, because rock phosphorus is rock. So more than 90% of land plants have a relationship with mycorrhizae. I think that's important to know. Largest organism in the world. The mushroom is the fruiting body. Nitrogen is needed in the highest amount, but it's not easy to retain in soils. So when we get to the soil sampling section, we'll look at some soil samples where maybe nitrogen is not included on the soil sample, and that's because it's so variable that it changes all the time. But it's not easy to accumulate nitrogen. So one way to manage nitrogen in your agricultural system is once you understand how much your soils can actually hold without leaching it, then you can apply that amount and do it in maybe if your soils leach, like say you are growing corn. Corn requires 125 to 150,000, 50,000. What am I saying? Let's just say 125 pounds of nitrogen per acre. If your soils are high sand, low CEC, they're going to leach that nitrogen very quickly. You're going to have to apply a very small amount over the course of many applications. If your soil is very high in clay and has very high CEC, then you could apply less often and more nitrogen, knowing that it's not going to leach. So those are some kind of rules of thumb. The other way we get nitrogen into the soil is thunderstorms, which is a fun one, because you can see how turf, grasses totally green up after a thunderstorm. Well, rain too, but I mean it happens faster and more so in a thunderstorm. And then through the bacteria of the legumes, which is rhizobacteria, and that's that symbiotic relationship. And they take nitrogen and the atmospheric nitrogen and they convert it into plant available nitrogen. And this process must occur in an anaerobic condition. So the plants have created this relationship with the bacteria by creating that tumor type of structure to create a oxygen devoid, I'm not saying that very well, an environment devoid of oxygen. So legumes are often used in agriculture. So, Change is Life by Harry McCormick, Sunbow Farm. I actually took a class from Harry McCormick, so I love seeing him on the film. We manage constant creation on a farm. It's a dance with nature. I love that. We manage constant creation on a farm. It's a dance with nature. So the clover is a legume that builds fertility. And this is a different farm where at peak they plow it in, and then they plant carrots, and then they plant oats. I remember this one because this guy really created a beautiful soil. And let's see, what else do I have in here? We are mimicking systems. So this is that point where Dr. Ingham talks about the strawberries, and if we're going to grow strawberries, wouldn't we grow them in the forest? Because they're actually forest plants. Wrong way. Oop, wrong way. What am I doing here? Going the wrong way. First time. All right, so then not Dr., but Mr. McCormick talks about how there are in a gram of soil, I think it was, there's 50,000 protozoa. Oh no, he was talking about a unit of soil. In a good unit of soil, which I'm not sure what exactly that would look like, but 50,000 protozoa, and every one of these 50,000 every one of them is consuming 10,000 bacteria a day, and their poop is nutrients. And the nutrients become the nitrogen reserve. And in a system that's cared for, where the soil is the primary focus and the organism that is that we steward, essentially, we could potentially have a reserve of 150 pounds per acre, which is enough to grow anything. And I said 125 per acre for corn. It's usually in between 125 and 150. Because nitrogen generally is the limiting factor. So because it's the limiting factor, that's when synthetic nitrogen came on board, but it came on board initially as an explosive, and then it was utilized as nitrogen for our agriculture, recognized as a saving grace by some of them, but the Green Revolution may not have been so green after all, now that we're on the other side of it and recognizing what went wrong there. And then the big historical event of the Dust Bowl is one of significance. I think there's another film in this class later on which highlights that, and it's worth watching. I mean, I think I make it part of your assignment, so you do watch it, but at the same time, it's really, there's some footage of it that's kind of mind-blowing. So a third of all arable land has been lost to erosion. And he talked about that spring mud run, that one farmer who had it literally in his house, and he decided there's got to be a better way to farm. So he started going with the no-till. He recognized that the good part of tillage is that it does spur on decomposition. So if you have a cover crop that you want to incorporate into the soil, well, then you have to till. But maybe it's not every year, maybe it's not every season, and maybe it's less often. Carbon is the driver, and more carbon in soil is always going to be better. There's never going to be a, oh, that's too much. It's always going to be better. The more, the better. So I actually had this conversation with somebody recently. It didn't really feel like a conversation, I gotta say. It was not necessarily very pleasant. I'm not really happy with, some things, or I'm not disagreeing with anything that was said. I guess I just didn't like the way it all came out. But it was an argument in which I made a very clear statement that there is fault in the typical organic farm, and that is because organic farms, even though I buy organic a lot, if I could buy it all the time, I would. If I could buy it from the neighbor, I would. If I could grow my own, I would. And I can grow my own, but currently I'm in a weird position where I, rent from someone with a very tiny yard. I will get there someday, whether it's through my job or on my own land or however that works. Maybe we're not supposed to have land, meant to own land, whatever. That was part of the conversation too. But the reason that some organic farms are not doing everything right and are still suffering from plant diseases is because nutrients, no matter what kind of farming practice you use, nutrients leave the soil. How? How do they leave the soil? Crops, flowers, herbs, grains. Well, that's crops. Veggies, that's crops. Every time you harvest, you're extracting nutrients. we're consuming some of these for our own nutrient benefit. So it's not even reasonable to think that extracting these things full of nutrients, you can leave the soil without inputs, right? So in some cases, organic farms and regular farms, obviously, are using regular inputs, fertilizers. It could be organic or not organic. The other way, let's just write these down, fertilizers. The other way is compost. But compost, unless it's like completely balanced and has every single thing in there that you've lost, it may not hold up. Which is why I really like in the Jerry Bernetti book where he is talking about adding the rock dust, and in biodynamics you're adding plant material and you're adding certain plants too. It's very, very conscientious as far as the plants that are being selected. It's also adding manures. I mean, manures tend to have more bacteria, and in an annual cropping system, we need more bacteria. So the inputs have to be there. Are there any other ways we add inputs? Well, if your compost, and this is the one fellow that was making the compost, if your compost is 50%, and this is what he did, 50% straw, which is carbon, 25% green matter, which is nitrogen, and then 25% was cow or buffalo dung, which is, in my opinion, the biology stimulator. And then he did, as well as the book says, adds rock phosphates as a biodynamic prep, which biodynamic preps are that incorporating plant materials, but very intentionally. It's not just anything. And then lime, and the way they described it was the lime keeps the nitrogen from flying off in ammonium. Ammonium is NH4, we don't want that. Even though plants do take it up, it's kind of like consuming sugar all the time versus protein. And then, you know, turning it the way it needs to so that it breaks down, so that the oxygen is there. We'll talk more about compost, obviously. I only say obviously because it's obvious to me. And adding that compost back. And in some cases, compost is a very expensive thing if you're not able to make it on the farm. It can be very labor intensive. Again, that's an expense essentially. If we look at our labor as a cost. So it can be put down on a very minimal level, but it can be put down on a minimal level, and if it has this this microbial kind of inoculant effect, then you may only need a small amount. And a small amount is better than nothing. So then there was another, the sheet mulch queen. The sheet mulch queen, that's about using sheet mulch and compost. Is a big piece of sheet mulching. We can talk about that obviously. And then compost tea. And this was where, I think it was in India perhaps, where, I don't know though, maybe not, I'm terrible at my geography and where people are from. We're all from planet Earth. The guy was making compost tea and he was turning it and he was mimicking the river. And I want to make, it makes me want to make compost tea right now. Whoa. So then the other fellow that was doing some good work in California, he would do a 2-inch thick layer of compost on his beds every year, and then he would put drip system in his beds, and he was using an hour of drip a week as opposed to 1 to 3 hours of drip per day. And this is one of the drier parts of California. And then the film went into Rodale farming system trials. Maybe we should go to Rodale. Maybe this field trip needs to go to Rodale. We need to talk about field trips. That might be a good one. I mean, that'd be a drive, but I'm willing to take that drive with you guys. I'm happy to carpool. But Rodale is a really awesome farm in Pennsylvania. It's not that far away. And they've had over 30 years of farming system trials where they're doing side-by-side trials of organic versus conventional, but they're looking at high input organic. So when you add this other layer to it, which is the biology, the regenerative agriculture piece, you're adding very specialized inputs as opposed to trying to, because when you're doing research, you have to eliminate as many variables as possible, and so that's why the high intensive input and the synthetic, the conventional is it's meant to be quite similar in a sense. But then we went into the whole no-till thing, and we will talk more about no-till because that's something that I think we're all going to be involved in as we move through agriculture. It just seems like the natural progression of our understanding, and then also introducing the animals back into the systems. And then it talked about eutrophication, which are the algae blooms, and that is from agriculture largely. The Gulf of Mexico dead zone is the size of New Jersey. And then I found this really interesting too, is that synthetic nitrogen contributes to 50% of the energy we use in agriculture. So just making nitrogen to put on conventional fields is 50% of the energy use in agriculture. And it's 50% effective because of the leaching. The cover crops can reduce that leaching, and again, in the Rodale Farm System trials, they're seeing that. And then the nutrient density is a piece that was covered by Klaus. I'll talk more about the food web. And then Dr. Fred Kirschman is Stone Barns. That's the other field trip, right? Blue Hill, we'll have the best meal of our life. Yeah, and then and then getting to the best economic model as far as farming goes is no inputs at all. And we will talk about that again. I mentioned Dr. Christina Jones. She has this really great thing on the phosphorus paradox. I want to share that with you when we get to the nutrient portion of this class because it's excellent. But she does say in one of her presentations about nitrogen that we may not get completely away from inputs of nitrogen, or no, let me take that back. She goes through a way in which over the course of 5 years we are weaning off of nitrogen, and because even in an organic system you add it because we're taking it away. We gotta eat, and the like say if you're typically using 150 pounds of nitrogen per acre, then the next year, I can't remember exactly, maybe it's 50% of that, the next year maybe it's 25% of that and whatever, and then at the end you're basically adding 5% of what you would have originally, and maybe that end goal is like at the 5-year mark, and maybe you do get away from it completely. But she did say that there could be a need for like a full year feed of 5% nitrogen over the course of the year, or over the course of the crop. And then it just went on to talk about a bit more about our current systems, which really have no resiliency. We've figured that out through COVID. I mean, this film was pre-COVID, right? But we've figured that out because transportation was broken down. And it wasn't even just in COVID, it was after COVID. I mean, there's just so many pieces of this global economy that fail when it comes to our needs, which our real true needs are food, shelter, water, air, and clothes and shoes are nice too, right? And then it went into a whole biofuels conversation because biofuels have a little bit of, or maybe a lot of controversy because people see that, to make the biofuels, we're using far more energy than we're getting in return. At the same time, there are other ways to make biofuels, and there are more efficient plants for biofuel creation. So I don't want to say that conversation needs to be over and done. I actually met a young person from Ideal Farms, and I want to go to he's having a makerspace festival. I'll share that with you guys. And it's just right here, and he started building his own biofuel converter, essentially, I suppose, when he was young in high school. I think he's maybe 30 now, and I just guessed from my conversation with him, but I would say he was using all cooking oil, so a result of like, you know, McDonald's or whatever. I can't even believe McDonald's still exists. I'm sorry if anybody here eats that, but I don't even know the last. I do actually know the last time I ate at McDonald's. The last time I ate at McDonald's was 2006. No. Yes. It was 2006 or 7. I was on a road trip with my friends, and we stopped there, and I remember eating that French fries and thinking they taste like chemicals. I never ate there again. I suppose if I was dying, I might, but I don't know. We'll see. Hopefully I'm not dying. So food resiliency is important, obviously, and that we can do by creating a community that is able to supply to our neighbors and our, you know, restaurants and our stores. Keeping it local. Farmers markets obviously are great, but we need to step it up a notch. And then Intervale, I loved that whole story about Intervale, Burlington, where they had increased their production to 10% in an area of Burlington that was like, you know, basically a wasteland. They've converted it into a beautiful farm and are supplying 10% of the town of Burlington, which I don't think is a town. It's quite a thriving little city. But soil was the fundamental resource, and local food movement is still and will probably always be very key in our ability to create resiliency in our region or our community, maybe more specifically our bioregion. Just knowing that bioregions are kind of separated from, you know, geographical things that may keep you from being able to so easily travel across the mountain or so easily travel across the river. So keeping it local, but accessible local, you know. There can be local that's not so accessible. Yeah, and we're kind of in a region like that because, you know, we could say Stroudsburg is local, but if you didn't have transport, you'd have to cross the Delaware River to get there and then go through some slight mountains. So really, Stroudsburg may not be a great idea as far as trying to keep your resiliency high. In that case, we would stay within our bioregion. And yeah, that's just what I wanted to cover, and it's about a half hour, and then I had a little number of, so this is about a 45-minute thing. Okay, hope you guys are doing well. Let me know if you have any questions, and I'll see you soon. Okay.